Hello everyone, welcome to the machine learning course. Please get ready. We are about to officially start our class, and I hope you all can gain something. Welcome back to our machine learning class. Today we're going to learn how to apply the decision tree algorithm to solve real-world problems. In this lesson, we will primarily focus on demonstrating the calculation process using the ID3 decision tree algorithms.
Let's quickly dive into the content for this lesson.
Let's consider an example. Our task is to determine whether a consumer will purchase a computer based on 4 features: age, income, occupation, and credit status. The age is categorized into 3 levels: income, 2-3 levels, occupations,
2 levels, and the credit status,
2-3 levels. Our target variable in this case is whether or not the consumers buy a computer, which has 2 possible outcomes. We have gathered a dataset to train our model for this purpose. We use the criterion of information gain to select attributes. In other words, to determine the nodes of our decision tree. Let's first consider how to calculate the information gains for the variable age. The following definitions we can create a table as shown, where the rows and columns represent the values of labels and the features, respectively. We can count the occurrences in each cell. Then, using the entropy calculation formula from information gain, we can compute the entropy value for each level of the feature. We use this entropy value to further calculate the conditional entropy. And from here, we can determine the information gain value based on the entropies and conditional entropy. We calculate the information gains for each variable in the step-by-step process, and ultimately select the variables with the highest information gains as nodes to expand our decision trees that we are constructing. The algorithm known as information gain utilizes the concept of average mutual information when selecting significant features.
The foundational theories of these algorithms is clear,
making it relatively straightforward. However, information gain calculations tend to favor features with a higher number of attribute values, which is somewhat unreasonable. ID3, in particular, exhibit sensitivities to noise. Furthermore, as the training dataset expands, the decision trees produced by ID3 will undergo changes accordingly. In
the Sklearn library, we utilize the decision trees classifier to isolate decision tree algorithms such as ID3.
Within this class, there are several important parameters we should be aware of. The criterion parameter is used to select the splitting criteria for nodes.
It can typically be set to entropy or Gini,
impurities, or entropies for information gain. The splitter parameters determines whether the splitting process is done by randomly selecting samples or by using all samples. You can set it to best for the best splitting or random for random splitting. Max features parameters controls the maximum numbers of features to consider when splitting nodes. You can specify it as integers or as floating point numbers. Max depths parameters set the maximum depth of the decision tree. Limiting the depth can help prevent overfitting.
The min sample split parameters set the minimum
numbers of samples required for a node to be further split. When the number of samples falls below this value, the node will not be split any further. It's a key parameter to prevent overfitting. These parameters can be adjusted based on the characteristics of your problem and the natures of your datasets to obtain the best performing decision tree model. Once the model is fitted, you can use it to predictions and the classification task. Let's dive further into the steps of building a classifier. First, that data splitting is to begin with. We partition the existing data with known categories into two parts, a train set and a test set. And next, we create a classification algorithms. Through learning from the training set, we develop a classification model. This model can take various forms, such as classification rules, decision trees, mathematical formulas, or others, to describe the patterns within the data. And then, using the obtained classification model, we validate this performance on the testing set. If the model meets the predefined testing requirements, like achieving a specified classification accuracies, we proceed to the step 4. If it doesn't meet the criteria, we return to step 2 to further refine the model or consider different algorithm. Once the model performs well on the testing set and meet the required criteria, we apply this model to test for data with unknown categories. This enables us to classify and make decisions about previously unclassified data. These steps represent a typical process for constructing a classifier. It helps us classify the new data based on the patterns learned from known data. Continuous model optimizations and validations enhance the classifier's performance and accuracy. When it comes to step 1, there are presently two primary methods. The first is holdout method. The holdout method entails randomly dividing the known data into two subsets, the training data and testing data. Usually, about 2/3 of the data are located for training, while the remaining 1/3 is set aside for testing. A classification model is built using the training data
and its performance in classifying.
The testing data determines the final classification accuracy. Another is k-fold cross-validation method. The k-fold cross-validation method entails randomly dividing the known data into approximately k equal subsets S1, S2 to Sk. The training and testing steps are repeated k times. There is iteration. One of the subset is designed as the testing data, while the rest of the subsets are used for training. Ultimate accuracies of the classifiers is calculated as the average accuracies across all k-testing instances. This approach is particularly useful for situations where the original dataset is relatively small, making the holdout method less practical. Classifier performance is typically evaluated using two metrics: recall and precision. Ideal classifiers should exhibit both high recall and high precision. However, these two metrics often conflict with each other, and there may be a need to strike a balance and make trade-offs between them, depending on specific requirements. So this concludes our today's course, and we will see you again in the next session.